Hello, I am Professor Yong-Won Song of Korea Polytechnic University. Title of my presentation is Analysis of Technical Evolution Trend for Predicting Future Technology. This is the contents of my presentation. At first, I will introduce the meaning of my research, and then I will show you 11 trends of technical system evolution. In conclusion, I will explain how to apply trends of technical system evolution to predict future technology. From the middle of 20th century, various future prediction methodologies such as Delphi technique and the future sphere were developed. Not only do these methods have limitations that many researchers spend a lot of time working together, but they also have the disadvantages of being involved in subjectivity of individuals or groups of researchers, which can lead to the false result. Therefore, it is necessary to develop a new future prediction methodology that can be easily used by individuals, and this new methodology should be objective. My approach is based on trees theory. Trees theory can be used to develop scientific future forecasting methods based on objectivity. TREES is the Russian acronym for Theory of Inventive Problem Solving. It is a well-established system of tools for inventive problem solving, idea generation, and prediction, developed by Russian scientist Altshuler. Altshuler studied the way technical systems have been invented, developed, and improved over time. He discovered several evolution trends that help engineers to predict what are the most likely improvements that can be made to a given product. He revealed that systems evolve not randomly, but according to objective patterns. But he used evolution trends mainly to solve the problem. But from 1980s, experts in the trees have begun to apply the technological evolution trends to future technology forecasting methods. However, the existing technology evolution trends were developed until the 1980s, and there is no analysis of development of modern industrial technology. In particular, additional analysis is needed, as there is no analysis on the technological development of the fourth industrial revolution. Therefore, this paper compiled the existing technological evolution trends and studied the new evolutionary patterns existing in modern industrial technology. And based on these trends of technical system evolution, I will try to develop new methodology to predict future technology. These are 11 trends of the technical system evolution. The first 9 trends are the result of research by Altshuler and his disciples. The other two trends were discovered through the latest technological development history study. First trend of system completeness of the part of the system. The technical system can be divided into 4 parts: engine, transmission, working unit, and control unit. A working unit is the part where the system performs the necessary functions for an external object. An engine is the part that converts external energy into the form of energy needed by the system to perform its function. Transmission is the organ that transmits the converted energy from the engine to the working unit. Humans operate the system through control units. The core organ of the system is the working unit, which first occurs when the system is born. As the system develops, engines and other organs emerge. So, technical system develop and to be completeness of the part of the system combined with the engine, transmission, working unit, and control units. The next slide we can see an example. It's the development of saws. First, saw blades were used to cut down trees. The rest of the roles, such as power engines, were performed by humans. As technology advanced, the power engine electric motor was developed, and the transmission and the control units were combined to become a complete system. Next trend of energy conductivity of the system. This is the system. The energy conductivity second trend of technical system evolution is the trend of energy conductivity of the system. Engine convert energy to the energy form needed by the system. So energy from engine to the working unit should be efficiently transported. As the system develops, the energy flow must improve. To improve energy flow, the energy conversion process and the energy transfer path are reduced. Let us see the example in next slide. Let's compare the energy efficiency of internal combustion engines and electric cars. In internal combustion engine cars, engine burn oil to heat energy and use expanding heat energy to turn it into piston reciprocating motion. Mechanical reciprocating motion energy is changed to rotary motion energy using crank and transmits rotational energy to the fields through transmission. Many losses occur during several energy conversion processes, making them less efficient. Electric cars, on the other hand, are directly converted from electrical energy to mechanical energy, which is transmitted to the field through a transmission. Electric cars are not only eco-friendly but also very energy efficient compared to internal combustion engines. So internal combustion engine cars will disappear and electric cars will be used mainly. The third trend of technical system evolution is the trend of harmonizing the rhythms of part of the system. The third trend is that materials, shapes, and movement of the components that make up of the technology system are developed in harmony with other components. It also developed to harmonize not only among the components within the system, but also with the surrounding system elements associated with the system. For example, a modern car has a damper that turns soft or hard depending on the condition of the road. The next trend of increasing the degree of ideality of the system. Ideality indicators can be used as a measure of the level of a technical system. Ideality is the sum of useful functions performed by technology system divided by the sum of costs and harmful functions. This trend is that the system develops in the direction in which the ideality increases. This trend is a key trend, very important trend that explains the developmental direction of the system. Consider, for example, the development of a wireless telephone. The first wireless phone was developed by Motorola Martin Cooper in 1980. The first mobile phone had a volume of 330 millimeter multiples, 44.4 and 8.8 millimeter, and weighted about 800 grams. This had only a call function, and with an 8-hour charge it could only make a call just for half an hour. However, modern mobile phones have increased their ideality such that they perform a variety of functions with very small sizes and less weight. Here we can see how many functions smartphones perform in modern technologies. Next, trend of increasing dynamism. The fifth trend is that the system develops from a static structure to a mobile structure that varies with the surrounding situation. As we can see in the picture, the ruler which measures the length was initially a long bamboo form, but developed into a form that could be folded with hinges, and developed into a form that could be rolled up using flexible materials. The same with the straw. The straw was first straight, but it developed into a comfortable bend. Next, trend of increasing the SU field involvement. This trend is that as the system evolves, SU field involvement increases. Here, SU field means the interaction between substances. Interaction between materials has mechanical, thermal, chemical, electrical, magnetic, and electromagnetic actions. The system uses various forms of a field or interaction to perform its function. In general, systems that use mechanic fields are developed at first, and the systems that use electrical, magnetic, and electromagnetic field are developed. It also develops from a system that uses only one field to a system that uses several fields. It's the sixth trend of technical system evolution. But consider, for example, the development of a material cutting system. People first developed and used mechanical cutting equipment. Next, equipment using thermal, chemical, electrical, electromagnetic method using laser were developed. It's the evolutionary trend. Next, trend of non-uniform development of system elements. System is composed of many components. Different parts of a system develop at different rates. Different components usually evolve according to their own schedule, meaning that the more complex the system is, the more uneven the evolution of its part will be. Different system components reach their inherent limits at different times, resulting in conflict. Elimination of conflict or contradictions allows the system to continue to improve. This is the evolutionary pattern. Next, trend of transition from macro to micro level. The eighth trend means that the working unit of the system changes as follows. The mono system develops into a B system, and the next into a multi-system. And also the working unit is generally made from a bulk solid material at first, but uses powder material as it progresses, and then develops into a liquid material or gas, followed by an electric field, a magnetic field, and an electromagnetic field. Let's see the example of this trend in next slide. As shown in the picture, the sail used in sailboat developed from mono system to B system and multi-system. And the propellers used in propeller planes also evolved from mono propellers to B propellers and multi-propellers. Next, example shows how working unit material change from solid to liquid and fields. This is an example of a cutting tool development. At first, the saw was made of a bulk solid but developed into a blade made by sintering the diamond powder or powder of strong materials. Next, water jet cutter using liquid water were then developed. Then plasma and laser cutters were developed. The history of print development is similar. At first, dot printers using a solid-shaped puncher were developed, after which inkjet printers using liquid were developed, and now laser printers are developed. Next, trend of transition to a super system. A technical system that has reached the limit of its evolution can continue to evolve at the super system level. After exhausting the possibility of development, system integrates to a super system by system merging or making hybrid system or becoming multifunctional system. Let's see some examples of this trend in the next slide. Here we can see hybrid system that combines solar and wind power systems. And right side is the hybrid bearing system. Ball bearings are advantageous at low speeds, but at high speeds there is a disadvantage of being worn out. Slide bearings, on the other hand, have advantages at high speeds. Each system developed independently and eventually developed into a hybrid system that combined each advantage. The next slide we can see multifunctional printers. Next, trend of increasing connectivity. The previous 9 trends are the technological evolution patterns that Altshuler, founder of trees theory, discovered through early research until the 1980s. He mainly analyzed Russian patents in machinery, materials, and aviation fields. Since then, however, the fourth industrial evolution industries such as IT, big data, artificial intelligence, and robot have been developing rapidly. So analysis of technological evolution trends in this area is very necessary. The 10th trend is that the connectivity of the systems increases. The number of devices connected was 1 million in 1992, but increased to 4 billion in 2009 and 34.8 billion in 2018. and by 2030 it will reach 125 billion. Eventually, everything will be connected with the help of Internet of Things. This is the 10th trend of technical system evolution. The last trend of decreasing human involvement. Technology systems are combined with artificial intelligence technology to develop into smart systems that perform functions that human wants. Systems developed to perform tedious functions that free people to do more intellectual work. Like the coming self-driving cars, this trend is the very powerful technology development pattern. Until now, I have shown 11 trends of a technical system evolution. In conclusion, I want to explain how to apply these trends to predict the future technology. First, take a look at Moore's law. Moore's law in the field of semiconductor is very famous technological evolution pattern and is effectively used to predict and plan the future of technology. As such, 11 technological evolution trends can be used to establish future technology strategies. A qualitative explanation on how to establish a future technology development strategy using technology evolution patterns can be found on the next slide. First, the level of the target system should be analyzed with 11 evolutionary patterns to identify the current level. This will allow us to identify relatively slow development directions. Based on this, we can develop a strategy to develop the technology in the direction of technological evolution that is lagging behind. This method has the advantage of being able to exclude the subjectivity of individual researchers and to establish objective and reliable strategies based on evolutionary trends. So we can make new methodologies to predict future technology based on objective trends of a technical system evolution. These 11 evolution trends can be useful for establishing future technology development strategies. But there is one thing to consider. Just as Darwin said that animals and plants evolve in a variety of ways, but that the species chosen by nature survives. The technology system can survive only when people choose. Therefore, we need to consider social trends as well as technical aspects. We should consider non-technical trends such as changes in people's lifestyles, social and cultural changes, and political trends. Therefore, it is necessary to develop a future technology development methodology that combines technology and non-technology trends. Thank you for your attention.